Hello and welcome back. Today I'm hoping to do something both simple and interesting. Now I really enjoy showing people this build and demonstrating its capabilities. Some people are very interested in the graphical stuff, others the games, but a subset of people are most interested in the very simple operations of the CPU, particularly when I slow it all the way down and single step instructions, and we can look at the way the data changes in the system. One particular demo I use for that a lot is the Fibonacci sequence, the first form of which was one of the first programs I ever executed on this system. But there is a question that comes up quite a lot, and today I'm going to show you that demo, talk about that question, and see if I can come up with a decent answer for it. So the CPU is sat at its command prompt waiting for input. At the moment it's running at full clock speed, which is 4 MHz, but I can slow that right down to trace mode. And even then, it doesn't seem to be changing very much. If I stop it to break, I can single step the instructions, and we can see it's running through a fairly simple loop where it's just checking for input on the serial port. Instead of doing that, let's load a simple program. Now this bit of code has done a little bit of setup, but then it's issued a break instruction which has switched the CPU down to single step mode. And this code is for demonstrating the computation of the Fibonacci sequence, which can be done with a very simple series of add operations. Let's step it. So first instruction we're seeing is an assignment to the A register. We've just loaded a 0 here into the constant register, and we've loaded it here, and nothing's changed because it was already 0. Now this next instruction coming in is an assignment to the B register, but here the constant loaded is a 1. So now we've assigned that into the B register. And here we see the fetch of the first operation in our Fibonacci sequence calculation. We're going to add B to A. So that's become 1. And now we have another operation where we're going to add A to B. So both A and B are 1. So that's going to become 2, which is the next Fibonacci number. We're back to adding B to A. 3. Adding A to B. 5. 8. 13. And then we can progress on. But in this code, I've inserted NOPs between the instructions, and from here on, I'm just going to add them back to back. So when we start to see the strength of the pipeline CPU, where it can do an instruction every cycle. 21, 34, 55, 89, 144, 233. And that's where we stop. Now the next Fibonacci number would be 377. And that's larger than I can store in an 8-bit register, and so this very simple form of the code doesn't work, and we need to move on to something more complex. But this is the bit where people are politely impressed, but they do ask, can you handle bigger numbers? So I show them this code. Now this version combines pairs of 8-bit registers to create 16-bit values and does the Fibonacci calculation with that. And I output the results to the console. The highest value we calculate here is 46,368, which is the 24th number in the sequence. 16-bit numbers, now they are twice as big as 8-bit numbers, but I don't think the maximum value there is going to impress anyone. And the total number of Fibonacci values we're able to calculate isn't very large either. And I'm a little bit worried I'm disappointing people with that. So I would like to look at ways of going bigger, and what I really want is to go a lot bigger. But before we can explore that, I'd like to experiment on C++ on a PC and just see if we can frame the problem a little bit clearer. So I've used the wizard here to create a very basic C++ file we can just start bashing code into. So I'm going to start working with 16-bit values. And then we need the value for n-2 and value for n-1. So we initialize those with the first two Fibonacci numbers at 0 and then 1. I'm going to initialize that one to 0 as well, because just to be complete. And we want to track the value we're on, and we're starting with the second value, so let's do that. We need a loop. So our basic Fibonacci calculation is very simple. The new value is equal to the previous value, n minus 1, plus the one before that. Let's output it. Let's use the same notation as my 16-bit assembly language version on the CPU. And we need a new line at the end. And then before the next loop, we need to roll these ones back. So n minus 2 becomes equal to n minus 1. Okay, so logically that's going to generate Fibonacci numbers and keep going. And it really does keep going. So I need a way of actually seeing the output there. So now we're generating exactly the sequence we saw on the CPU when single stepping it. That's as far as we got, but we can go on beyond that. These numbers are getting a lot bigger, a lot quicker. And that's as far as we got on the 16-bit version, but now we've overrun. So we need to detect that and stop. So I'm just going to detect if the new value is smaller than the previous one, which is going to happen when we wrap around. That's okay, but we want to do that test before we output the value. That's better. So we've recreated the 16-bit version, but we're running on a PC here. Let's see if we can move up. An unsigned int should be 32 bits. We've got to the 47th value here. Quite a bit bigger, but it doesn't feel that big. Let's go up to a 64-bit value. So we're generating 20-digit numbers, and that's the 93rd number in the Fibonacci sequence. But I would like to go a lot further than that, and these are 64-bit values, so I'd have my work cut out making this run on the CPU. Here's my code for the 16-bit Fibonacci sequence. It's actually quite simple. The most complicated math operation we do at the high level is just adding numbers together. But we are calling the output functions, and most importantly we call this function, which converts a 16-bit value to a human-readable decimal value. I could extend the add out to do an almost arbitrary sized operation fairly easily, as long as I can fit it in memory, but a bigger version of this is difficult. Let's go and have a look at the code. So I'm doing this with a series of 16-bit divides, which was handy because I explicitly wanted to write that divide operation and built a video around showing the programming of that. But I've only written divides up to 24 bits. And as the numbers get bigger, divide operations get more complex, especially when you've only got 8-bit registers. And so that's going to be the real impediment to creating a Fibonacci number generator which generates massive numbers. Now there is an algorithm called Double Dabble which assists in doing the conversion to decimal without using divides, and I have used that here for a 32-bit version of I2A. But if we look at the code for this, the outer loop I do 32 times, then I've got the dabble operation and the double operation. That's a unrolled shift, but that's quite a few operations, and the dabble is quite a few instructions if you don't have any custom support for it. So this algorithm's worth reading up on, and I'm particularly mentioning it here because people will talk about it in the comments if I don't. But even this feels like overkill for the kind of operation we want to do. So we've seen we can even have a problem on some modern programming languages, at least using the internal types. Now on the CPU, we've already looked at how we can chain together 8-bit operations to make bigger numbers, and we could extend that into quite large values. But we do hit this problem where we've got a complex task to turn those values into decimal to make them human readable. And how are we going to solve that? What we're going to do is turn the problem on its head. Instead of trying to solve the binary to decimal conversion, let's keep the values in something closer to decimal, and we're going to use BCD. We've got a more difficult add operation, but then the display is going to be simpler, and that's going to enable us to make much larger numbers a lot easier. Let's take a look. So I'm starting off with some code I've created just by stripping the guts out of a copy of the 16-bit Fibonacci code. So down here I'm just outputting the title. So we need our values. We start one value on 1. Now I'm going to store each BCD entry in a byte. That's not the most efficient way of doing it. Normally you see 4 bits used, so 2 values in a byte, but it's going to simplify the code for me to do it like this. I can improve it later once it's working. And I'm going to do 256 byte values. So that will give me space for 256 digits. So we've got 2 values. We're starting one with 1 and the other with 0. And that's the same as the 8-bit version. Now we want to add 1 to the other. So I'm imagining I've got a function called BigNumAdd, which will take parameters as pointers in SI and DI. So we're going to do the same as in the 8-bit version and alternate the directions, and that will create the Fibonacci sequence if we repeat it. So if we do that 500 times, we're going to get 1,000 values out. I want to format it the same way we did before. So we're going to need a counter. We'll use AB as a 16-bit index calculation. Need to do that between each. Displaying the index, we're not going to break 16 bits very easily, so we'll just do that and use the standard function. And now we're going to need another function for doing the numerical conversion. We want to output A on this loop. Let's call it that, to ASCII. And this is exactly the same, but we're outputting B. That's actually all the code we need to do 500, apart from we actually need to write these big num functions. Adding 2 numbers together in this binary coded decimal notation shouldn't be that difficult. Let's save off the registers. We're going to want that there as well. Right, that will loop 256 times. Okay, right, this logic is quite simple, even though it won't work. We load a byte from SI, we load a byte from DI, add them together and store it. And in the simple case where the numbers don't overflow 10, that's going to work. But what we actually want to do is wrap it at 10 and preserve the carry. So we're going to have a potential carry value from the previous operation. We start that at 0, but then we add it in. So in theory, A and B could have been 9 and carry could have been 1. So A is anything from 0 to 19, and we want to make A, or we want the carry flag to be equal to A divided by 10. We want A to equal A mod 10. So we need to detect that carry. So I'm going to initialize B to 246, and that is 256, which is one larger than the biggest number we can store, minus 10. So if we add A to that, then the carry flag will then be the carry we want. And in that situation, B will be A mod 10. That's cool. So we can then put that value into A, and we can just increment D to give it that carry value. And then we store that, and I think that's everything we need to do the add. Now, it is quite a bit more complex than the binary add, where we'd just be doing successive versions of add and add with carry, but this does scale quite linearly. See how much easier this is. I'm creating a string, and I need room for a terminator. If I just do this one character at a time, I'm going to end up with a large number of leading zeros. So I think what I want to do is scan through and find the last non-zero value. So we read a byte in. If it's not 0, I want to store the index. I think life will be easier if we save off the address of the last non-zero as well. So by this point, B should equal number of digits, since that's the index of the last non-zero digit, and DI will be the address of the last non-zero. Need to handle the case where there is no non-zero, so let's start that there. And C is 0 based, so we need to increment B. Right, so we're moving backwards through from the address of SI. We want to add to that the ASCII value for 0. Hopefully we've got the spare register. Store that. Is it that simple? We do need to stick a terminator on the end. Okay, that feels like we've done everything. Well, it assembled okay. Let's give it a test. Oh, that didn't work. Let's see if we can work it out. This should be the address of value A, and that's definitely got data in it, so we should be seeing an output. So the problem must be in this function. Okay, LOD_SB is going to move SI on 1. So we actually need to remove that from DI to be pointing at the right location. Still nothing. So this is the temp string memory, and that looks like a valid number. Why is that not getting printed? That doesn't explain why we get nothing out, but that does. Not actually outputting the string. Right, I'm going to be less bold and let's output 30 numbers initially. That looks more promising. So there we go past the 8-bit range, and we sail past the 16-bit range. And there's very little to stop us going further. Let's be bold and put that back to 500 for 1,000 values. Hey, look at that. So I can see that spent a lot of its time just maxing out the UART write speed, and we have outputted the first 1,000 Fibonacci numbers. I've just double checked that against the website that has a large number of Fibonacci numbers just to confirm it's correct, and it is. That's awesome. That was fun. That last number was 209 digits long, and it's the 1,000th Fibonacci number. And of course, it wouldn't be that big a code change to go vastly beyond that into the thousands of digits. So the system of flipping the calculation on its head and having a slightly more complex add operation, but a much simpler conversion to ASCII, was a big success. Really hope you found this interesting. As always, a big thanks to all my patrons and supporters, and everyone else. Don't forget to like and subscribe. I'll hopefully see you again soon. Goodbye.